So 8.6 is about the structure of acids and bases and how you can recognize where the important groups are for those acids and bases. Okay, so the protons on a molecule that will participate in acid-base reactions and the relative strength of these protons can be inferred when you look at the overall molecular structure. So strong acids, we know, have very weak conjugate bases that are stabilized by electronegativity, inductive effects, resonance, or some combination of those. So this is why they will completely dissociate, because they are very weak conjugate bases. They're stabilized by electronegativity, resonance, or some of those effects. Okay, this is reasons why. Now, weak acids, most of them are what are known as oxyacids or carboxylic acids, where an acidic proton is attached to an oxygen atom. Or sometimes it might be another highly electronegative atom if it's not oxygen, but oxy is for the oxygen part. Okay, so I have two examples, acetic acid and benzoic acid, that both have this structure where they have a hydrogen connected to an oxygen. And so the hydrogen out here would be the acidic proton. Okay, and so all the other hydrogens within the compound are not acidic. Only these oxygens connected hydrogens would be. Okay, this group right here is actually called, this is a carboxylic acid group for organic chemistry, that if we have time for, we might talk about that a little bit later this year, that is on organic molecules. So you can look at a structure and look for all of these acidic protons, and I've seen questions, and you might run across questions that have acidic protons like that based on the structure connecting to oxygens. Strong bases, just to review, we talked about those already. They have hydroxides with group 1 and 2 metals. So they have a very weak conjugate acid. They completely dissociate and are very stable because of the fact that the conjugate acid is very, very weak. Now for weak bases, they include nitrogenous bases, like nitrogen-containing molecules, as well as carboxylate ions, which I have pictured here, are carboxylate ions, excuse me. So electronegative elements will tend to stabilize the conjugate base relative to the conjugate acid, and this is then what increases acid strength. When you see where the higher electronegative element, then that means to stabilize, makes it stronger, okay? Now, electronegative elements, just to review, those are the halogen column on the periodic table. They're group 7A. So in order, that would be fluorine, chlorine, bromine, iodine. So fluorine is the most electronegative of all of the atoms because it has the greatest affinity for electrons, okay? And so when you're trying to compare, when an acid or a base has these electronegative elements in them, the stronger the acid or base, then it would need one higher up in the column. Okay, so anything that contains iodine or bromine would be a lot weaker than acids or weak bases that contain fluorine or chlorine. So we have this example to practice. So we have 3 scenarios, 3 diagrams, 1, 2, and 3, with weak acid, its conjugate base, and hydronium ion. And we're comparing 3 different acids, HIO, HBRO, and HClO. So HClO, you might remember from chemistry 1, is hypochlorous acid. HBRO is hypobromic acid, and hypoiodic acid for the other 2. But names are not that important. So Each particle diagram shown is a representation of an aqueous solution of one of the acids listed. The molarity of the acids in the solution is the same. So based on this information, if they all have the same concentration, which particle diagram best corresponds to the indicated acid? So for all 4 of these choices, only one really corresponds to any of them. So on all of the acids, they all have, they're all weak, and they all have these electronegative parts to them, electronegative elements to them. Okay, so if we go back, it looks like from the pictures, the more hydronium you have present, that means the more dissociated it is. Okay, so picture 3 has the most hydroniums. So that means that this would be the strongest of all possibilities. And then picture 2 only has 1 hydronium. So that would be the weakest of all of the options. Well, knowing what we know about the electronegative atoms involved, iodine is at the bottom, chlorine and fluorine are at the top. So that means that the hydrochlorous, or the hypochlorous, will be the strongest because the chlorine is the most electronegative. So that one would dissociate the most, okay? So I would say that diagram 3 must be the HClO, okay? Then the weakest would have to be the lowest electronegative out of all of the column, which would be the one with iodine. So diagram 2, I would say, contains the HIO. Okay, so then by default, diagram 1 must be the HBRO. Okay, so now let's look at our options and see which pairs up correctly. Okay, so we said that diagram 1 was the Br containing acid, and so that makes A not correct. Diagram 2 contains the Cl acid. That is not correct. Diagram 2 contains the HI. Yes, that is correct. And diagram 3 corresponds to the Br containing, and that is a no. So it has to do with C. So again, it has to do with that, the electronegativity of the halogen atom involved with the acid, and acids get weaker as the electronegativity decreases down the column. So this is just a quick video. If you want more information on this, you can watch the AP Daily videos on AP Classroom for this, or the following sections. They are listed, and your textbook would also be good reference points.